we were just computing the posterior distribution on the W vector under linear regression. We were doing Bayesian linear regression, and we got the posterior distribution on W given the data. And things went kind of quick there at the end, so we need to tie up a couple loose ends here. So the first thing was that, well, let's check this little fact here just to go over why this implied that this was the distribution. Let me fix this. I should have put W here instead of X. So I hope you weren't too confused by that, since we were using X for something else entirely. This should be W. And so a multivariate Gaussian in W is proportional, the density is proportional to e to the minus 1/2 times this, times something that looks like this, where this lambda is it's called the precision matrix, and it's just the inverse of the covariance matrix. So if we were to, so we solved for what we needed lambda and mu to be, and if we were to plug those in here into this expression, and then you multiply it out, then we would get something which was equal to this plus a constant. Just by our choice of lambda and mu, we chose them so that this would be equal to this plus a constant. And that just means that e to the minus 1/2 times this is proportional to e to the minus 1/2 times this. And here I mean a constant with respect to W. So when I say proportional, I mean proportional as a function of W. Alright, so hopefully that was clear as to why this works. I find this a really handy trick because, for me at least, I always make mistakes when I'm trying to complete the square and I get confused. But if you write it out this way, at least for me, it's just crystal clear, and you can just match up these expressions. So I hope you find that a useful trick also. And let's put these mu and lambda over here to bring everything together, and then in a sec we're going to check that lambda is in fact invertible. Actually, let me plug in what lambda is here. No, we'll leave it that way for now. Lambda inverse A transpose Y, and lambda is A transpose A plus BI. Okay, so this is what we think is going to be our posterior distribution, and we just have to check that this lambda that we chose is actually invertible in order for this to make sense. So this is going to be our posterior. And let's check let's do a little calculation here. I think here's how we can check this. So this is just a little calculation. So let's say that B is some matrix. Let's use a different color. Okay, so B is some matrix. This is just in general. We have some matrix B, let's say it's a square matrix. And let's consider B plus some constant times the identity matrix. That's what this lambda has that form. This would be B, and this would be, well, I put C, but some constant times the identity matrix. And we want to see if this is invertible. So in order to do that, I'm thinking ahead, and I'm thinking about the eigenvalues of this guy. I know that this guy is positive semi-definite, so I want to say that when we add this, that we only increase the eigenvalues, and so the eigenvalues are going to be strictly positive. But let's check and let's check that. Let's verify that. So let's say that if U is an eigenvalue, or rather an eigenvector of B, and lambda is a corresponding eigenvalue, then we have BU equals lambda U, and U is also an eigenvector. Any vector is an eigenvector of I, so CIU equals CU. And so, okay, so we're getting it now. So if we add these together, let's see. So B plus CI times U is, of course, BU plus CIU, and that's lambda U plus CU, and that's and that's just lambda plus C times U. So this shows that lambda plus C is an eigenvalue for B plus CI with eigenvector U. And so C, right, so okay, so we've got it now. So B was a strictly positive number. Remember, B was the precision. Where do we put that? Let's see, B. Right, B was the precision here, and B was strictly positive. So C here, if this C is strictly positive and lambda is greater or equal to 0, so this shows that if lambda is greater or equal to 0 and C is strictly positive, then, of course, lambda plus C is strictly positive. And this holds for any eigenvalue of B, right? For any eigenvalue of B, we get another, and the corresponding eigenvector, we get a new eigenvalue and eigenvector, where the new eigenvalue, well, the eigenvector is the same, and the new eigenvector is strictly positive, right? All of these, the eigenvectors were non-negative because A transpose A is positive semi-definite. And that just means, right, so A here is positive semi-definite. I mean, not A. A transpose A is positive semi-definite. Actually, A times A transpose A is positive semi-definite because little a is a strictly positive number, so that doesn't change the fact that A transpose A is positive semi-definite. And positive, I keep saying positive semi-definite means that the eigenvalues are greater or equal to 0. All the eigenvalues are greater or equal to 0. That's the definition of, or one definition of, positive semi-definite. And so we get this. So that means, this little calculation here implies all this. So let me just use a different color. So all of this implies that lambda is invertible. Why does it imply lambda is invertible? Because if all of the eigenvalues are strictly positive, then it's invertible. The determinant, one way to check that something is invertible is you look at its determinant, and the determinant equals the product of the eigenvalues. So if all the eigenvalues are positive, then their product is positive, and so it's invertible. All right, so I just wanted to go through that explicitly so you would see, just so we make sure everything is above the board here. Okay, so we got this posterior, and that's excellent. Always want that for Bayesian inference. And okay, so now one thing we can immediately get from the posterior, this is a cool immediate consequence. This is neat. So we can immediately get from the posterior, in this case at least, since this is a Gaussian, we can get the map estimate immediately. Because what is the map? The map is the maximum a posteriori, that is, it's the value of W that maximizes the posterior distribution. And the maximizer for a Gaussian distribution is the mean. That's an easy thing to check. So the maximizer of a Gaussian distribution, the mode, you could also say, of a Gaussian distribution is the mean. So let's not prove that here, but I'm sure it's an easy calculation to check. So that shows us that the map estimate of W is, W map is mu, right? It's just this mu right here. So let's write out what that is. A times lambda inverse, and let's plug in what lambda inverse is. Lambda inverse is little a times A transpose A plus BI. Let's write that. Little a times A transpose A plus BI. Inverse times A transpose Y. And now let's simplify this a little bit. Let's move the A inside. If we move a constant inside a matrix inverse, it just becomes 1 over that on the inside. That's just a little fact you can check if you want. So it becomes, so we move this inside and we get 1 over A cancels this A. And we get B over A times the identity inverse A transpose Y. And that gives us a nice expression for the map. Sorry, my timer's beeping at me. And that gives us the map. And if you remember from when we computed the MLE, let's write the MLE and we'll see the similarity here. This is a nice way to sort of remember what the map is. The MLE was A transpose A inverse times A transpose Y. And if you compare these two, it's easy to see that the only difference is in the map. We add inside this, before taking the inverse, we add B over A times the identity times the identity matrix. And this B over A here, so this gives you, in comparison with the MLE, remember this was also the pseudo inverse. The MLE is the pseudo inverse of A times Y. We talked about that when we talked about the MLE. And you can easily remember how to get the map, what the map is, by remembering the MLE. Now this B over A here, this is sometimes called the regularization parameter or constant. And the reason for that, and sometimes you call that, I don't know, sometimes, well, people use different names. Sometimes they use lambda for a regularization parameter, but we were using lambda for something else here. And regularization is, in some sense, it's a little bit more general technique. It's for most of the time, regularization is equivalent to putting a prior and then computing the map estimate. But in cases where there is not a proper prior, and there are such cases, then, or there are cases in which the regularization, putting a regularization, the kind of regularization that you might choose, does not correspond to a proper prior. That's the way I should have said it. You can choose a regularization scheme which corresponds to an improper prior. And so in some sense, regularization is a little bit more general than if you were to say, strictly speaking, using a proper prior. It's a little more general than Bayesian, well, it's not really fully Bayesian. It would be sort of half Bayesian, since you assume a prior and then you get the map. And regularization, the difference, so let me just tell you briefly, the difference is that you would just try to minimize some loss function, and the loss function that you try to minimize is basically the exponent here. So this part here is your regularization term. You're regularizing with respect to, this is the norm squared of W. So you're regularizing with respect to the squared norm of W. So I just wanted to point that sort of connection out, so you know, if you hear about regularization, what that means.